Chapter 1.7 we'll be doing combinations of functions and composite functions. So before we get into that, let's just recall what domain is of a function. So the domain of a function is going to be the set of numbers that can be plugged in for x. So domain is going to be the set of x values that when we plug them in result in real numbers. So there's a couple different types of functions here. The first one being polynomials. So for polynomials, the domain is all real numbers. So negative infinity to positive infinity, we can plug in any x values and it's not going to be breaking any math rules. The other one is rational functions. So rational functions are going to be a ratio of polynomials. So a fraction with a polynomial in the numerator, polynomial in the denominator. The domain for rational functions is going to be all real numbers, except the x values that make the denominator equal to 0 because we can't divide by 0. And then for square roots, for the third one, the domain is going to be all real numbers except the x values that make the radicand a negative number. Because for now, we can't take the square root of a negative. We'll be doing that in several weeks, though. Okay, so let's do these examples. Let's find the domain of each function. So the first one is f of x is x squared minus 7x. So in order to find the domain, it helps to know what kind of function it is. So this is a polynomial. It's a polynomial because the terms are separated by addition or subtraction, and they have positive whole number exponents on the variable. The domain of every polynomial is all real numbers, so negative infinity to positive infinity. So those ones are pretty easy. Next one, we have g of x is 3x plus 2 divided by x squared minus 2x minus 3. So this is a rational function. And it's a rational function because it is a ratio of polynomials. So for a rational function, what we do is we say that denominator cannot equal 0. And then we just solve it like we would if it were an equal sign. So what we do here is we factor that left-hand side. We factor that as x minus 3 times x plus 1. We say that cannot equal 0. So what we do at this point is we set those factors equal to 0. So we think, unless you want to write it out, we think x minus 3 equals 0. So this is something called the zero product property. Something times something equals 0. One of those things has to be 0. So if x minus 3 equals 0, that means x has to equal 3. And if x plus 1 equals 0, that means x has to equal negative 1. So this means that x cannot equal negative 1 or 3. So I'm going to write this in interval notation. So the domain is going to be all real numbers from negative infinity to negative 1. Union negative 1 to 3. Union 3 to infinity. So essentially this just means everything but negative 1 and 3 because there's parentheses there, so it's not including negative 1 and it's not including 3. Next one, h of x is the square root of 3x plus 12. So this is a square root function. So based on what we had written in that paragraph above, we said that the radicand has to be greater than or equal to 0. It cannot be negative. So when you're solving these, what we would have to do is we have to isolate the x, subtract 12 on both sides. We get 3x greater than or equal to negative 12. Divide both sides by 3. We get x has to be greater than or equal to negative 4. So the domain for this one is going to be negative 4 to infinity, and we have a bracket on the negative 4 because it could be or equal to it. Okay, last one's going to be actually a little bit confusing. So j of x is 3x plus 2 over the square root of 14 minus 2x. So this is not a rational function because the square root is not a polynomial. So what I'm going to write here is just that there is a square root in the denominator. So originally what we would say, ignoring the fact that it's in the denominator, we would say the radicand 14 minus 2x would have to be greater than or equal to 0. Since this is in the denominator, it cannot equal 0, so that means this strictly has to be greater than 0. And then we're going to solve this the same way. I'm going to add 2x to both sides and get 14 greater than 2x. Divide both sides by 2, and we would end up getting x is less than 7. Okay, so the domain here is going to be everything less than 7, so that's negative infinity to 7 with parentheses because it's not or equal to. Okay, so that's a quick refresher on domain and the domain of those certain functions. So for the next thing, we're going to go over the sum, difference, product, and quotient of functions. So we kind of know how to do this already, but we have different notation. So f and g are going to be functions here. And the sum, difference, product, and quotient are going to be functions where the domain is going to be the set of all numbers that's common to both the domains of f and g. So here's the new notation. So if we were adding two functions, f of x plus g of x, instead of writing it like that, we can write it as f plus g of x. Same thing with subtracting. Instead of f of x minus g of x, we can write it as f minus g of x. For multiplying, instead of f of x times g of x, we can write it as f times g of x. And for dividing, instead of f of x divided by g of x, we can write it as f over g of x. So all that is new notation, and we'll see in a second how we pretty much already know how to do this. So for example, let's let f of x be 2x minus 1, and g of x is x squared plus x minus 2. So for the first one here, let's find f plus g of x. So if it helps you, you can write this like this, f of x plus g of x. All we're doing is adding these functions together. So it's going to be 2x minus 1 plus x squared plus x minus 2. So this is combining like terms. So it's going to be x squared, 2x plus x, so plus 3x, negative 1 plus negative 2, so minus 3. So all that is combining like terms. Same thing for this next one. We have f minus g of x. So if it helps, we write it out as f of x minus g of x. And we have 2x minus 1 minus x squared plus x minus 2. So we could have gotten away in the last one without putting parentheses around it. This one we need parentheses around that second polynomial because of that negative. So I'm going to distribute the negative and get negative x squared minus x plus 2. And now we just combine like terms again. So it's negative x squared plus x plus 1. So that's f minus g of x. Okay, next one, f times g of x. So for this one, that means we're multiplying, so it's going to be f of x times g of x. So that's going to be 2x minus 1 times x squared plus x minus 2. So we have to distribute, right? We have to distribute the 2x into every term in the second polynomial and also distribute negative 1. So distributing the 2x, we should get 2x cubed plus 2x squared minus 4x. Distributing that negative 1, we should get negative x squared minus x plus 2. Now we combine like terms, and we get 2x cubed plus x squared minus 5x plus 2. So went through that kind of fast because we should already know how to do that. And lastly here we have f divided by g of x, which is just f of x divided by g of x. So all we have to do is say that that's going to be 2x. We plug in for the functions once again. 2x minus 1 over x squared plus x minus 2. So technically we should take into consideration when g of x is 0. So if we took that denominator and factored it and set it equal to 0, we would see that x cannot equal negative 2 and it cannot equal 1. So we can't even do anything to this, so it's actually just as simple as dividing them and leaving it just like that. Okay, for the next one, let's say we have f of x is the square root of x plus 3, g of x is the square root of x minus 2. We want to find f plus g, and we want to find the domain. So f plus g is going to just be adding these together. So it's going to be the square root of x plus 3 plus the square root of x minus 2. So that's actually the answer. We cannot simplify that any further. So the difficult part here is figuring out that domain. The domain of f plus g of x, the domain of this sum, is going to be the interval that the domain of f of x and the domain of g of x have in common. So let's figure these out separately. So the domain of f of x here for the square root of x plus 3 has to be greater than or equal to 0. If we isolate that for x, we're going to end up getting x has to be greater than or equal to negative 3. In interval notation, that's going to be negative 3 to infinity. So I'm just basing this off of the information from that first page. So for the next one, for g of x, the square root of x minus 2, x minus 2 has to be greater than or equal to 0. Solving that for x, we're going to get that the domain is from 2 to infinity, including that 2. Okay, so if we want the domain for the sum here, f plus g, like I mentioned, it's going to be the interval that these two domains have in common. So let's do a little number line for the domain of f of x. 0. So from the domain is negative 3 to infinity, including that negative 3. Put an arrow. And let's do a number line for the domain of g of x. We said that that was from 2 to infinity. So that's going to be like this. So the interval that they have in common is actually only going to be from 2 to infinity. So it's where they overlap. So that's going to be the domain for f plus g of x. Okay, so those are things that we've pretty much done a lot of already with the sum, the difference, product, and quotient. So the next thing should be relatively new. So it's composite functions. So this is going to be another way to combine two functions. So what this kind of means here is that it's taking one function as the input to another function. So we're inputting a function into all of the x's in another function. And the way that we can write this is with that little circle, f of g of x. And we can also write it like this, f of g of x. And then we read it just how I said that. So the domain for this is where it gets a little bit harder. The domain of the composite function is going to be all x values, such that x is in the domain of g of x, and g of x is in the domain of f of x. So it seems a little confusing, but we'll hopefully clear it up once we do an example in a page or two. So let's do this example. So let's say we have f of x is 3x minus 4, and g of x is x squared minus 2x plus 6. So let's find f of g of x. So composite function, so it's going to be a function as an input to another function. So if you want to, you can rewrite it like this. So we're going to, f of x is our main function here. So we go over to f of x. Everywhere there's an x, we put a g of x. We're plugging g of x in to f of x. So it's 3 times g of x minus 4 instead of 3x minus 4. And now let's actually plug in for g of x. g of x is x squared minus 2x plus 6. Make sure you have parentheses around it. And then all we have to do here is simplify, so distribute and combine like terms. So 3x squared minus 6x plus 18 minus the 4. Lastly, combine those like terms at the end. We get 3x squared minus 6x plus 14. Okay, so as a function as an input to another function, so let's do another one. Let's do g of f of x this time. So this time we're going to be plugging f of x into g of x. So starting with g of x, we know g of x is our outer function. It's x squared minus 2x plus 6. Everywhere there's an x, let's plug in an f of x. So it's going to be f of x squared minus 2 times f of x plus 6. And now let's actually plug in for f of x. So 3x minus 4 squared minus 2 times 3x minus 4 plus 6. So we have to simplify this. So 3x minus 4 squared, you would have to FOIL that on the side. 3x minus 4 times 3x minus 4. That's going to give us 9x squared minus 24x plus 16. I'm just going to show where that one came from. So that all comes from that. And then distribute that negative 2. We get minus 6x plus 8 plus 6. And we combine like terms. We get 9x squared minus 30x plus 30. But it's 30 because I accidentally wrote 6 when it should have been 16 right there. So plus 30. There we go. Okay, so that notice that that is not equal to f of g of x. So here's f of g of x. Here's g of f of x. They are not the same thing. So let's evaluate g of f of 1. So if we want g of f of 1, we actually have g of f of x, right? We have g of f of x right up here. So that's the function for it. All we have to do is plug in a 1 to that function above here. So it's going to be 9 times 1 squared minus 30 times 1 plus 30. So that's going to be 9 minus 30 plus 30. The 30's cancel. So this actually just gives us 9. So there's another way to do that. We actually had g of f of x. So in order to find g of f of 1, we just plugged it in. So it's pretty simple. So the other way to do it is use the fact that, so I'll put or, we're going to use the fact that g of f of 1 equals g of f of 1. So what this means is we would evaluate f of 1 first and then plug that value into g of x. So f of 1, what was f of x here? I'll just kind of do this one out loud. F of 1, f of x is 3x minus 4. So f of 1 would be 3 times 1 minus 4. So 3 minus 4 is negative 1. So we would plug negative 1 into g of x. So g of negative 1 would end up giving us 9, which is the same thing that we got over here. Okay, so let's do another one. So given f of x is 2 over x minus 1 and g of x is 3 over x, let's find f of g of x and the domain of it also. So f of g of x, we're plugging g into f. So f is the main function, so it's 2 over x minus 1. Instead of x, it's going to be g of x. So 2 over g of x minus 1. And then let's actually plug in g of x here. So it's 2 over 3 over x minus 1, plugging in the g of x. And for this, what we would have to do for this is a complex fraction, a complex rational expression, what we could do is multiply the numerator and denominator by the least common denominator of those three terms, 2, the 3 over x, and the negative 1. That would be multiplying the numerator and denominator by x. When we do that, we would end up with 2x divided by 3 minus x. It has to get distributed to both terms in the denominator, so the x's cancel for 3 over x, and then negative 1 times x is just negative x. Okay, so this is our f of g of x. So now for the harder part with the domain. The domain, we have to look at g of x, and we also have to look at our f of g of x. So for the domain of g of x, g of x equals 3 over x. So x cannot equal 0 because it's in the denominator. So in interval notation, this would be negative infinity to 0, union 0 to infinity. So that just means all real numbers except for x equals 0. And then we also have to look at the domain of our final answer. The domain of f of g of x I'm going to write this a little bit differently. I'm just going to write domain of our simplified result. So that's going to be the domain of that answer that we just got. So that's a rational function. It's a polynomial over a polynomial. So the only value we can't plug in here is something that'll make the denominator equal 0. If we plug in x equals 3, that'll make the denominator 0, which we can't do. So it's going to be all real numbers except for x equals 3. So this is going to be an interval notation, negative infinity to 3, union 3 to infinity. So the domain of our final answer here, the domain of f of g of x, so this is why I didn't write it for the previous one, I replaced it with simplified result. Domain of f of g of x is going to be a combination. It's going to be both of those together. So it cannot equal 0 and it cannot equal 3. So it's going to be negative infinity to 0, union 0 to 3, union 3 to infinity. So that's the domain of that composite function. So kind of complicated, I guess. You just have to take into account both of those domains. The one that you're plugging in, which was g of x, and then your simplified result after you plug it in. Okay, so for the last thing here, it's decomposing functions. So for decomposing a function, we were just doing composite functions. So decomposing is going to be the opposite of composing a function. It's going to be the opposite of a composite function. So we're going to start with a function that's going to be a composite function, and then we're going to rewrite it as a composition of two functions. There's always going to be multiple ways to do this, which I'll show us. There's going to be an easiest way, which we should always do it this way. The easiest way is to let g of x equal the inner function and f of x equal the outer function, and then our answer is going to be f of g of x. So let's see what we mean here. So let's express h of x as a composite of two function. So h of x is the cube root of x squared plus 1. So if we want to express this as, let's say, f of g of x, so we want h of x to equal f of g of x. So that means we need f of x and we need g of x. So I'm going to say, let's let, like I mentioned up in the notes up here, g of x is going to be the inner function. The inner function is just x squared plus 1. And f of x is going to be the outer function. f of x is the outer function, it's going to be that cube root. When we're doing this, all we have to do is the cube root of x. So you replace that whole inside with just x, and that's it. So that is actually it. So h of x is going to equal f of g of x, put where g of x equals x squared plus 1, and f of x equals the cube root of x. So let's check this to make sure here. So if we want f of g of x, which is f of g of x, we're going to plug in g of x into f of x. So it's going to be the cube root of x. So the cube root of g of x, we're plugging in g of x, which is the cube root of x squared plus 1, which is what we wanted. So we know that that works. So when I mentioned there could be multiple ways to do this, what we could have said here, so put or, we could have said, so h of x was the cube root of x squared plus 1. We could have said that f of x equals the cube root of x plus 1, and g of x equals x squared. So to check this, to make sure that this works, f of g of x, we plug g of x into f of x, that would be the cube root of g of x plus 1, which would be the cube root of x squared plus 1, which is what we wanted, because that would equal that h of x up there. So there's always multiple ways to do this by kind of pulling that little trick by adding one and subtracting one, but it's not the easiest way to do it, so I'm gonna erase it. Okay, so just know there's multiple ways to do it. So let's do one more, except let's only do this the easy way, so it seems a lot more simple. So let's express h of x as a composition of two functions once again. So let's say we have h of x. We want it to be a composition of two functions, so f of g of x. And we want f of x to be something and g of x to be something. So g of x, let's just let g of x be the inner function, which is x minus 3. And that means that f of x is the outer function, which is something to the 4th power. So it's just going to be x to the 4th power. So to check, it's going to be f of g of x is going to be g of x plugged into f of x. So it's g of x to the 4th power, which is x minus 3 to the 4th power, which is what we started with, so we know that we chose correctly. Okay, so that's actually it for 1.7. So it was essentially just new notation for adding, subtracting, multiplying, dividing functions, as well as composite functions and decomposing functions.